Hi everyone. Today, we're diving into a really cool topic, visualizing the imaginary roots of a function using Mathematica. We often think about where a function crosses the x-axis, those are its real roots, but what about roots that involve imaginary numbers? Our focus today is the function f x equals cos x, cosh2 x. This function looks quite innocent, but it hides a fascinating set of imaginary roots that we're going to uncover and visualize. First, let's quickly consider the real roots, which are much easier to find. Real roots are where f x equals 0 for real values of x. We can simply plot f x using plot cos x cosh x caret 2 x minus 5 5. Looking at this plot, we'd see that f x is 0 whenever cos x equals 0. This happens at x equals pi/2, pi/2, 3 pi/2, and so on. The cosh2 x part never becomes 0 for real x because cosh x is always greater than or equal to 1. So, the real roots are straightforward. Now, let's tackle the main challenge, visualizing the imaginary roots. An imaginary root is a complex number x equals u plus 4 where I is the imaginary unit, I caret 2 equals -1 for which f x equals 0. When x is a complex number, f x also becomes a complex number. For f x to be 0, both its real part and its imaginary part must be 0 simultaneously. This means we need to find u and v such that f u plus 4 equals 0 and I'm f u plus 4 equals 0. Mathematica provides a powerful tool for this, ContourPlot 3D. We can use this command to plot the two conditions separately and then observe where their surfaces intersect. Here's how we set it up in Mathematica. We define our function f x underscore equals cos x cosh x caret 2. Then, we consider x as u plus iv. We need to plot f u plus iv equals 0 and I'm f u plus iv equals 0. The ContourPlot 3D command will look something like this. ContourPlot 3D, cos, u plus iv, cosh, u plus iv, caret 2, equals 0, I'm, cos, u plus iv, cosh, u plus iv, caret 2, equals 0, u, minus 5, 5, v, minus 5, 5, z, minus 1, 1, plot legends dash automatic, axis label dash real part of x. Imaginary part of x, dummy z. In this command, u represents the real part of x and v represents the imaginary part of x. The z-axis is just a dummy variable. We use it to create a 3D space where our two 2D conditions can be visualized as intersecting surfaces. The actual imaginary roots are the points in the UV plane where these two surfaces cross each other. When we execute this plot, we'll see two distinct surfaces. One surface shows all the points u, v, where the real part of f, u plus 4, is 0. The other surface shows all the points u, v, where the imaginary part of f, u plus 4, is 0. The true roots of f, x, are precisely where these two surfaces intersect. You'll notice lines of intersection. For our specific function f, x equals cos, x, cosh caret 2, x, we will see the real roots u, 0, from cos, x, equals 0 lying along the u-axis, where v equals 0. But crucially, we will also see purely imaginary roots 0, v, from cosh x equals 0. The cosh x function is 0 when x equals I, pi/2 plus n pi, which are purely imaginary values. These will appear as intersections along the v-axis, where u equals 0. You will also observe more complex roots, which are combinations of both real and imaginary parts, appearing at other intersection points off the axis. This visualization vividly demonstrates how real and imaginary roots coexist and how complex functions behave. It's a powerful way to map out where a complex function equals 0 in the complex plane. And there you have it, a journey into visualizing imaginary roots using the incredible capabilities of Mathematica. It helps us look beyond the familiar x-axis and truly understand the behavior of complex functions. Thank you so much for watching this video. I hope you found this exploration both informative and visually engaging. If you enjoyed this content and want to see more mathematical visualizations and explanations, please consider subscribing to the channel. Hitting that like button also helps a lot. It supports us in creating more videos like this. See you in the next one.